saw the base drive circuit 1 where we had used an NPN BJT. Along similar lines, we can also use a PNP BJT. It is the dual of the NPN circuit. The PNP BJT also is quite popular in base drive circuits, as you will see when we develop other base drive circuits. Now here you have this emitter, base and the collector, and the PNP is rail driven, that is positive power supply driven. In the case of the NPN, it was driven with respect to the ground because the emitter was connected to the ground. Here the emitter is connected to the positive of the power supply, so the drive is rail driven. But the circuit is exactly similar. Between emitter and the base, have this resistor, that is the positive supply. I'll have this resistance between the emitter and the base. Even in the NPN circuit, between base and emitter, you had a resistance, but only now that resistance is connected to the positive rail. And between the base and the signal source, you will have one more resistor. And you have the collector flowing into the load. As before, in the case of the NPN, the collector was connected to the load. So you have this IC, the collector current, which is the load current. And let's say the transformer has a HFE SAT, some value. IC by HFE SAT will be just the saturation value. You have to provide IB on in the base drive so that it goes deep into saturation. So IB on is 2 times IC by HFE SAT. So that value should be given here. R1 and R2 are the two resistances that you need to design, and IB on is what you should give here. So how do you choose the value of R1 and R2? Well, this is VBE SAT. Like in the NPN circuit, R2 is given by VBE SAT by an equal amount of IB on flows through like this. You have IB on flowing through in this fashion, in this direction, and VCC minus this potential divided by R2 will be the current flowing through this, and that current should be IB on. 2 IB on will flow through R1. Now R2, let us calculate R2. R2 equals VCC minus this potential is nothing but VB SAT. So the VB SAT divided by IB on will be VB SAT into HFE SAT divided by 2 times IC. Same like in the case of an NPN drive circuit. Now if you have VB and VB is the signal voltage, so this will go low. When this goes low, then there will be a current IB on flowing through R2 and IB on coming in from the base. 2 IB on flows through R1 and sinks into the signal source. When VB is high, this potential will match the potential here, and there will not be any flow of current in this direction. So when VB is high, the BJT is off, PNP BJT is off, and when VB is low, the BJT is on. Okay, so let us say you have an IB on coming from here and IB on coming from here that will flow through R1, and that current will be 2 times IB on. Now what is the value of R1? R1 is this potential minus this potential. And what is this potential? This potential is VCC minus VB SAT will be this potential. Let me write that down. VCC minus VB SAT minus VB, that is the signal source potential, will be the potential which is occurring across R1 divided by 2 times IB on will be R1. So IB on is nothing but 2 IC by HFE SAT. So I will say HFE SAT divided by 2 into 2 IC 4 IC. So this will be the equation for finding out R1 in the case of the PNP drive. So this is exactly the dual of the NPN drive, and many cases, many complex drives are built from these two drives. NPN, PNP they complement each other, and many stages can be achieved by this NPN, PNP combination. We will of course have a look at this combination complementary drives later. The simple base drive circuit, just two resistors in the base, NPN and PNP base drive circuit, are very popular and used in many base drive circuits. Let us see if we can apply them to our DC-DC converters. Now let us take the simple non-isolated buck converter. It is something like this. Now here on the rail side, on the positive side, let me put a PNP transistor like this. If you are doing it on the ground side, you can use an NPN transistor. So let me put this PNP transistor and let me complete this buck converter circuit by putting this diode, inductor, capacitance, resistance, and then you are taking the output across these two terminals. This is VI and this V0 measured in these two fashions. Now for the PNP base drive circuit we just now saw, from the emitter to the base, let us put a resistor. There is a resistor from the emitter to the base, and from the base to VB, that is the source from where the signal is coming, we put another resistor. So this is our simple 2 resistor base drive for PNP, which is driven from the rail. This is a positive. This is R1, this is R2, and this is VB. Now what to give here for VB? Let us see how we can give VB. In fact, to make this a practical circuit, I can recommend that you try implementing this. It is possible. You just take a 15 volts laboratory power supply. This will be your 15 volts input. You can design for a 5 volts output. You can use a 2N4033 BJT transistor. This is a PNP transistor, easily available. Then a diode, you can use a FR304 diode, easily available in the common electronic shops. You can use a 1.5 millihenry inductor wound on a core. You have to design and wind it on a core, put a 100 microfarad capacitor, and then that's it. You are having almost all the components. And for I0, you can design I0 in 5 milliamps to vary between 5 milliamps and 500 milliamps. Max is 500 milliamps. So the resistance here is known. Now what do we connect here? And then at what frequency do you switch this BJT? So let us put that down. Switching frequency of the BJT 20 kilohertz. So almost everything is ready except that we need to give the pulse width modulated waveform here at VB. So we had looked at how to generate pulse width modulated waveform some time back, and I had also told you that there are commercial ICs available. One such IC is TL494, Texas Instruments TL494, very inexpensive, around 10 rupees or so. You should be able to buy that and use it. So let us make the connection for TL494. Let us say pin 12 is VCC pin and 7 is ground pin. Let me connect the ground, and for the pin 12 ground means these two are joined together, and this is VCC. So let's say this is VCC, and let me connect VCC to VI. So VI itself, unregulated VI itself, will be the power supply for the TL494, 15 volts. Next, I will connect two important components, a resistance, timing resistance, and a timing capacitance to pin 5 and 6. So a timing resistance RT and a timing capacitance CT, these are precision components, use a metal film resistance here and use a metallized polyester capacitor for timing. And if you want 20 kilohertz, you use one typical component value for resistance is 5.6 kilo ohms, and CT is 10 kpf. There are various other possibilities you can use. From the data sheet, you can look at nomograph and pick up the values of RT and CT. Next, let me give something to vary the duty cycle. So I will use a potentiometer and two resistances in this fashion. A resistance, fixed resistance connected to VC, fixed resistance connected to ground, and in between I am having a potentiometer. So this is the variable resistance. It will this center tap will vary from a particular minimum resistance to a maximum resistance here, and I will have a voltage here in between such that it is between the sawtooth. If you measure at pin 5, you will get a sawtooth waveform, so that the voltage here should be in between the sawtooth waveform. So connected in that fashion, this we can say 1K, 5K and 1K. This is connected to pin 1. Pin 2 and 3, now 1, 2, 3 is an error amplifier. Pin 1 is the positive input and 2 is the minus input and 3 is the output. So you can short 2 and 3 to make it in the voltage follower mode. There is also another amplifier which we can disable. So let us say 4 this is the DTC or the dead time control pin. There is a steering pin and the other error amplifiers positive. All these let us ground it. We don't need it now, ground it. And the plus of the other amplifier, the minus of the other amplifier and the output of that one we short it just like here in the emitter follower or the voltage follower mode. Now that is 15 and 14. Now internally there are two transistors that will get enabled or disabled depending upon the pulse width modulated waveform that is coming to the base internally of these internal transistors. So this is pin 11, 10, 8 and 9. You can use any one of the transistors. Now let us say I use this 8, 9. 8 is the collector, 9 is the emitter. Ground the emitter and the collector, let me connect it here. So that's it. You have a PWM generator IC where the duty cycle can be varied and it is controlled, and at this collector you will get pulse width modulated waveform which is given as get base drive signal to this PNP BJT, which will switch this buck converter and you will get the required output. Now this is a open loop control of buck converter and it can operate as designed. R1 and R2 you know how to design it, we just saw while designing this PNP base drive. So how does it operate internally? When this internal transistor turns on, you will see that this will be shorting. The collector will be connected to the emitter and the VB will be at ground potential ideally. So there is a path for IB on to flow here and IB on to flow here. 2 IB on flows through R1 into VB and into the ground and complete the circuit. Now let us say the internal enabling pulse is removed for the internal transistor. This is open. When this is open, pin 8 is floating. So there is no chance of current to flow through. Current IB on can't flow here. BJT is off. So in this way BJT can be turned on or off by controlling the internal enabling pulse to the internal transistor of the TL494. But our focus here was to just demonstrate to you how the base drive works. This is a simple base drive, 2 resistance base drive and a PNP. If you use the ground side switching, you can use a NPN transistor and 2 resistor base drive. However, as you start going higher in power, you will need more complex base drives, and that's what we will look at further.